right. Welcome to the lecture on Introduction to Parallel Computing and High Performance Computing in Phylogenetics. I'm Alexandros Stamatakis. Right, so here's the outline of the presentation. I'll first give an introduction, then I'll give you an overview of parallel architectures. Then we'll quickly go over maximum likelihood again. So basically about the computation of likelihood scores. We're going to talk about parallel likelihood computations, and finally I'll talk a little bit about how you go about obtaining CPU time on large supercomputing systems. Okay, so here is probably something that you all know. That is Moore's law that tells us that approximately the number of transistors on processors doubles every about 18 months or something like that. But of course, after the year like 2000, 2005, the number of transistors on a single chip so did not double anymore, but we just added more and more cores to a single processor die. So this is something to keep in mind, that for keeping up with Moore's law, at some point we started duplicating cores, meaning that even at the normal level, at the laptop or desktop level, we need to use parallelization, parallel computing, to fully exploit our hardware. The other graph that you probably all have seen before is the so-called bio gap. So here, this is the cost on the y-axis, this is the cost of computing, or cost of sequencing a genome over a time axis here. And what you can see clearly is that, well, Moore's law has remained constant, right? So the cost of computing is dropping at a decent rate according to Moore's law, but the cost of sequencing a genome has been dropping much more rapidly. So we have this kind of gap between the cost of computation and the cost of sequencing. So this year is, I think, with the introduction of nanopore sequencing technologies and packed biosequencing technologies. So this means that we basically have a problem that we're generating more and more data, but we don't really have the capacity or the funds available for analyzing that data. Okay, and so this is what I mentioned before, the so-called multi-core revolution. Of course, this took place a couple of years ago, presumably when most of you were still going to school. But this shows us that, well, the performance increases through frequency increases stopped, right? So when I was going to university and to school, every year we were getting CPUs with higher clock frequencies, meaning that more arithmetic operations could be performed per second, and they kept increasing and increasing and increasing. But at some point we hit a plateau, so the clock speed plateau, meaning that for various physical reasons and electronic reasons, we cannot really improve the clock speed much beyond 3 gigahertz. And so that's when people just started adding more cores to CPUs, meaning that we need to apply parallel computing. Okay, let's start with some basics. So who knows who Gene Amdahl is? Probably just one or two, I guess. This was a computer pioneer, and he came up with this law about parallel computing that kind of explains to us why parallel computing is not trivial, or just adding more cores. Like adding 2 cores will not make your computer run twice as fast. So let's look at Amdahl's law and what it tells us. Assume that you have a program here, a computer program, that consists of one sequential part that is shown in red because it's kind of bad, it cannot be parallelized, and one parallel part that is shown here in green. So you may think of that like as a phylogenetic inference program, like RAXML. So the sequential part is the part, for instance, where the alignment is read from file, and then the green part is the part where we actually do parallel likelihood calculations. So we say that we consider here that, well, the sequential part takes 10 seconds and the parallel part takes 128 seconds. So if we now use two CPUs, and in an ideal case where our parallelization is really good, so it halves the time for the parallel part, we can actually see that, well, the parallel part is reduced by half, but the sequential part still stays the same. So if we continue doing that, so instead of two CPUs we use four CPUs, then you can see here that, well, again, the parallel part is cut by half, but the sequential part still remains constant at 10 seconds, right? So now the sequential part takes up almost as much time as the parallel part. And then finally, if we add 8 CPUs, once again, or if we use 8 CPUs, the parallel part now takes 16 seconds and the sequential part still takes 10 seconds. So what this graph actually tells us is that the degree of parallelization or of parallel efficiency that we can achieve is somehow limited or constrained by those parts of the program that we can only execute sequentially, right? So if we keep adding more and more cores, what will dominate the runtimes is just like the input file parsing or the program startup or things like that. So the bottom line here is, as every program has some inherently sequential part that cannot be further parallelized, at some point the execution times will be dominated by the sequential part of the code. So this is very important, meaning that, if I have 200 cores and I have a parallel program and I run it on those 200 cores, it will not be 200 times faster. Right, so here's like just another graph showing Amdahl's law. So on the y-axis we have the so-called speed up, which basically tells you what I just said, right? So if I use 10 cores, ideally, this red line here is the linear speed up. I want it to run 10 times faster. And if I run the code on 30 cores, I want it to run 30 times faster. So this is like the ideal world, or what we call linear speed up. And then the thing that we consider here is the following. So those p-values here give us like the part of the code that is parallel, right? So p equals 1 is a linear speedup, so everything in the code is parallel. And then we add some sequential fractions to the code. Say that 5% of the code here, like p.95, 5% of the code are inherently sequential. You can see here how this affects the speedup, right? Like already at 10 cores, we have a speedup of around 7 or 8. And then at 30 cores, we have a speed up of around, 12 or something like that. So even if there's only like 5% of the code that cannot be executed in parallel, we already have like a substantial drop in parallel efficiency. So once again, this p-value here just denotes the fraction of the code that can be optimally parallelized, right? So here we're assuming that the parallel part of the code can actually be ideally parallelized, meaning that every time we double the number of cores, the execution time of that parallel part drops by half, which is in practice rarely the case. Okay, so now I'll just give you like a brief overview of our parallel computer architectures, because it is important to know what kind of architectures we're running our codes on. So if we consider parallel architecture, some of the key questions are: what is the network speed? How do I actually synchronize concurrent operations? How do different cores communicate with each other? And how is memory organized? So basically, we'll do this bottom up, starting at the CPU and then looking at more increasingly complex computer architectures. Right. So here now we consider parallelism within a single CPU. So even within a single CPU, we do have parallelism. And this parallelism is given by vector architectures or vector operations. So they have like weird, nerdy names like SSE3, AVX, AVX 512. And what vector instructions actually do is that they execute the same operation, the same mathematical operation or arithmetic operation, simultaneously on more than one value or data. Um, so if you wonder what GPUs are, why I'm not covering GPUs, essentially GPUs are also just vector processors, but they do have like an extremely large vector. So you can, on GPUs, you can execute the same arithmetic operation simultaneously on a huge number of values. Whereas in normal CPUs, the number of values you can simultaneously execute a vector instruction on is typically limited to, say, 16 or 32. Also depends on what kind of data structure you're operating on. Right, and so here's how vector instructions work. So for instance, in RaxML and RaxML-NG, we do have dedicated versions of the software that use SSE3 and AVX vector instructions that are basically present or available on all modern CPUs. Right, and so clock tick in our processor means that we're executing one instruction. So for instance, if we have a clock CPU with a frequency of 2.2 gigahertz, this means that we're able to execute 2.2 times 10 to the power of 9 instructions per second. Okay, so let's now consider how those vector operations work. So assume we have a vector A and a vector B that have elements 0, 1, 2, 3 and 0, 1, 2, 3, and that we want to execute a vector, an element-wise addition of those elements in the two vectors. So the result of the element-wise addition will be stored in C and is of course 0, 2, 4, 6. And now if we execute this sequentially without the use of vector instructions, this operation will require, well, 4 clock ticks, right? So I first have to add the first two elements and store them, then the second two elements and store them, the third two elements and store them, and the fourth two elements and store them. Now, if we have a vector unit of size or of width 2, so if we have a vector unit, we always talk about the width of this vector unit, meaning how much data it can actually take in. Right, so, and if I have a vector unit of width 2, well, I can do those two operations simultaneously because I'm applying the same arithmetic operation to the first entry of to the first entries of vectors A and B, and to the second entries of vectors A and B, and then I'm also storing them here. So I can do this operation simultaneously with one cycle, and adding the second part, the elements of the second part or the second half of those vectors can also be done in one cycle. So here, instead of requiring 1, 2, 3, 4 cycles to do this operation with a vector unit of size 2, we actually only need 2 cycles to complete this operation. So it kind of became twice as fast. Right. So we can also use vector instructions for parsimony calculations. So there is a little code I've written many years ago which is called Persiminator, and this code actually does use vector instructions, and maybe now I will just do a live demo of this. So let me move that here. Let me find the directory. If I'm able to. Just wondering where where this is. Shouldn't take me too long to find it, hopefully. Okay, so now I finally managed to find the code, and so what we're going to do is that we're going to measure execution times of different versions of this persiminator. So we have one here, persiminator, that doesn't use vector instructions at all. And then we have two versions of persiminator that persiminator AVX and persiminator SSE3 that use vector instructions. So basically, the difference between AVX and SSE3 is that the AVX vector unit is twice as wide, so should ideally be twice as fast as the SSE3 vector unit. So here what we're going to do is that we're going to do a little tree search on an alignment with 125 taxa and around 30,000 sites. We should give this run a name, and the other thing that we're showing here is that we need here is that like a random number seed, right? So we're passing the alignment to the program, the random number seed, and we give it a name, and we can also use this time command to measure how long it will take. So this, now we're just running a tree search under parsimony that has not been optimized, and we see that we had this required 6.459 seconds. Okay, so now let's run the SSE3 version. Let's change the name of the files, see how fast that is. Well, so here you can see that it's already kind of half the execution time, so now it took 3.134 seconds. And finally, let's run the AVX version. It should be even faster. Well, it's 2.877 seconds. So normally you would have expected that it runs twice as fast, but this is not the case. So do you have any idea why that is? So here again, what we're actually seeing is Amdahl's law, right? Because the program runs so fast, 2.877 seconds, that actually the computations that have been parallelized using those vector instructions do not really represent such a large fraction of the program, because we also have like the input parsing, etc., etc. So if you run the AVX version on a larger data set, where the actual computations take up a larger fraction of time, then you would actually see a larger speed up. So maybe this is some sort of homework where you can actually test that. Okay, but let's get back to the slides. So we did a little demo. Okay, so let's get back to vector instructions. So vector instructions are available on standard CPU architectures, so standard x86, Intel or AMD CPUs. Typically we have vector widths of 128 or 256 bits, so this is SSE3 and this is AVX. And as of 2017, there are also 512-bit instructions available on Intel CPUs. I already mentioned GPUs being large vector units or vector processors, and their vectors are typically at least one order of magnitude larger. One cool thing is that vector instructions are somehow synchronized automatically by the processor clock. So after a clock tick, I know that, like as in our example, both parts of the results have been written concurrently. So this is just synchronized by the processor clock. So I don't need to think about the validity of the entries. Okay, so this basically means that there's no synchronization overhead, and the conclusion is when you're running a program and you're doing a large-scale analysis, you should always check and use SSE AVX or AVX 512 versions of the programs. So there are some problems with using vector instructions. Problem number one is that to leverage the power of vector instructions, we actually need highly regular numerical operations, meaning that we need to typically do some sort of linear algebra operations or statistical operations on vectors. The problem number two that we've experienced with RaxML is that we might not be able to get the data into the CPU quickly enough to leverage the increased processing speed. So this is something we've observed with a 512-bit vectorized implementation of likelihood calculations on phylogenies, right? So because if you use vector instructions, what this means is that you can process more data per second or more data per clock tick. But this also means that you need to get more data into your processor in order to be able to leverage that additional computational power. So frequently your computational limitation may not be the processor speed or like the computing power of the processor, but the speed of the memory subsystem that allows you to move data to your CPU that you need to do operations on. Okay, so now we're moving one step up and looking at parallel architectures. So one typical configuration of parallel systems that these days we typically have on our laptops and desktop computers is that we have shared memory, right? Like we have two or more cores that are connected to the same main memory and can therefore also communicate or exchange data and results through that shared memory. So both are kind of connected to the RAM. And typically, like the typical paradigms for shared memory programming are either pthreads or OpenMP. And you may think of threads as lightweight parallel processes that communicate over shared memory. Right. So what happens in the real world? There's something that we didn't talk about so far, and those are the so-called cache memories. So assume that this is your processor, this is CPU 0 on which we're running thread 0, and this is CPU 1 on which we're running thread 1. And then in order to get stuff, meaning data, more quickly into memory, each CPU has this, what we call like a level 1 cache. So this is kind of a smaller and faster, much faster to access memory than the main memory. And the reason why this is called cache is that the idea is that it should hide the latency from this for memory accesses from the CPU to the main shared memory, like the random access memory. So here's how that works, or here's how cache memories work. So we have the CPU has a very fast connection to this intermediate memory cache that caches or hides the latency to the main memory. Then we have relatively slow link between the cache and the main memory. So this cache memory stores data that we frequently operate on. It has faster data access, but also smaller memory capacity. Those are the important things. Right, so the question here is, well, is it such a cache memory useful for a program or an algorithm that conducts totally random memory accesses all the time? Maybe think about this for a second. So our CPU is just kind of doing random memory accesses all the time, like requesting data from random positions in main memory all the time, or from random addresses. So in that case, the cache memory is not useful, because every time the CPU asks for an address in the cache, we'll see that the data is not stored here or cached here because it's random access. So it will be forced to go to the main memory to fetch this data. Then so the cache requires two things to work properly. One is something like fixed pattern of memory accesses. So for instance, linear memory accesses, or memory accesses as you would do them in a matrix multiplication. And it also, to really work well, it also needs us to do a lot of operations on the data that is stored in the cache memory, right? So we want to um, be able to do as many computations on the memory of the subset of the addresses that from the main memory that are stored in cache before moving them out to the main memory again. So this is the abstract view, right? Like we have a CPU, cache memory, and a main memory. And this is actually the real world um, where we do have several level of caches. So this is also called the cache hierarchy between the CPU and the main memory. And the further we go out, the larger the capacity gets, but also the slower the memory access speed gets. Okay. So here's an interesting example how caches can affect the efficiency of parallel programs or programs in general, right? So assume that the size of our level 1 cache here is 10 megabytes, but the overall RxML memory footprint, so the memory it needs to store conditional likelihood vectors, the alignment, the tree, etc., is 20 megabyte. So if we're only executing our tool, like RxML for instance, on one single core, well, those 20 megabyte of data do not fit entirely into the cache, right? Because like another 10 megabyte need to reside here. But we're not using the additional core, and more importantly, for this example here, the additional memory capacity offered by the other level 1 cache. So now if we're using 2 cores, all of a sudden we have not only doubled our computing capacity, but also our cache memory capacity. So if we're using 2 cores on a run that requires 20 megabyte and each core has 10 megabyte of capacity, then 10 megabyte will entirely fit into this cache here, and the other 10 megabyte will fit entirely into this cache here. And so this is great because there's no need to communicate with the slow main memory. And this means that actually our parallel program may even run twice as fast as a sequential program, just because we are doing less memory accesses to the slow and large main memory. Okay, then here's just like an idea. Well, I want to give you an idea of how much communication and synchronization is taking place in RxML when we're doing parallel likelihood calculations. So here we're computing the likelihood for a single tree concurrently on many cores, so the multiple sequence alignment has been distributed to many cores. We're just computing the likelihood of a single tree. So for just for 10 seconds of runtime using 16 cores, a dataset with 400 taxa and 7,000 sites requires almost 200,000 synchronization points, like synchronizations between the two threads, and a dataset with 1,500 taxa and 1,200 sites requires 740,000 synchronization points where the threads communicate with each other, make sure that they are at the same position in the code. Right. So here are some questions for you to think about. So given 16 cores and a large alignment, here in this example, we compute one single tree, the likelihood of a single tree on 16 cores concurrently or simultaneously. So why shouldn't we compute, just like do 16 independent tree searches on 16 cores? Why shouldn't we do that? Or why wouldn't that be better? So what do you think? Just think about it a little bit. And the other question I also have for you is, why do we synchronize more frequently on this data set with 1,500 taxa within 10 seconds of runtime than we do for this data set with 400 taxa? Okay, so maybe some answers to that. So why shouldn't we compute 16 trees on 16 cores? Well, we may actually put a lot of memory pressure on the system, right? Because um, if you'd assume that the single tree analysis requires 100 megabyte of main memory, then if we had 16 trees, this would require 1600 megabyte of main memory. So we're using much more memory, meaning that we can probably not get a very efficient use of the cache memories because we'll always be waiting for the main memory. So basically here we somehow want to reduce the memory footprint of our analysis, and rather, if we want to do 16 tree searches, do one tree search after the other, and every tree search using the 16 cores. And the reason why we synchronize more frequently for 1500 taxa is, as I said before, we're kind of distributing the multiple sequence alignment sites over those 16 cores. So here, for 1500 taxa, each core will have less than 100 sites to work on. So basically individual calculations are much faster until the processor reaches the next synchronization point. I hope that this is somewhat clear, otherwise we can discuss it in the discussion section. Okay, so now we're kind of moving one step further up. So we've talked about parallelism within a core, parallelism among cores, and now that are connected to shared memory. Now we're also going to talk about the large systems that are interconnected by a network. So typically this is a node in our compute cluster that is connected to shared memory. And this is connected via some sort of interconnect, typically InfiniBand or gigabit Ethernet or something like that, to another node here, like to another shared memory system. And so that's what we call distributed memory. The typical programming paradigm here is the MPI, so the message passing interface. Here what we use per node, per shared memory system, are heavyweight processes that communicate to each other over the network by sending and receiving messages. So this is how it works. So if we talk about distributed memory, this guy here, so the CPU here, cannot access the memory of the other guy, like the partial results of the other CPU, directly by going directly to its memory, but it will have to go over the network and explicitly request for that part of the memory. And so that's what it does. It sends a message to the other CPU that, of course, needs to, at the same time, execute a receive message and will then send the data back to the requesting CPU. So this is like the send-receive paradigm that we use here. And the key questions, if I'm thinking about a parallel compute cluster, are, well, how fast can I establish a connection? So those are the properties. Now we're talking about the properties of the interconnect network. So how fast can I establish a connection? This is latency. So this is very important if I'm communicating very frequently, but if I'm not exchanging a lot of data, right? So then my communication times will actually be dominated by the latency, so how long it takes to establish a connection between two nodes. And question number two is, well, how much data can I actually transfer per second? So this is if I'm have to exchange large amounts of data. Now, considering some communication schemes between processes or between nodes, there's one communication scheme we call direct communication. Then there's another communication scheme that we call broadcast. So here one processor or one node distributes or broadcasts its data to all other nodes. Typical example here is that you would say that, well, this node here, or process number 0, actually parses the multiple sequence alignment and then broadcasts the sites on which the other processors should work on to those processors. And then there's like the reverse operation, which we call indirect communication or reduction, where one processor collects typically partial results from all other processors. So a typical example here would be that, well, they all did likelihood calculations on, let's say, so processor 1, processor 2, processor 3, on 1/3 of the alignment sites, and now to compute the overall log likelihood, some processor needs to collect those partial likelihoods and compute the overall log likelihood score of the tree. Right. So here's an overview over the hierarchy, or how we discuss this in a bottom-up way. So first of all, we have this kind of heavyweight process that is executed on a typically shared memory node. And within this heavyweight process, we've got like a couple of threads running that are occasionally synchronizing, then maybe a single thread continues working, etc., etc. And then, so those are the threads, and then this is the thread synchronization, this line here. And then within each thread, because typically each thread is executed on a separate CPU, we have those vector instructions, right? So there's kind of this type of very fine-grained, low-level parallelism, which is vector instructions. Then we have thread-level parallelism. And then in the end, we have this MPI-based parallelism, or send-receive-based parallelism, where process 0 and process 1, that are both running a couple of threads, both executing vector instructions, are exchanging messages over the network. Right, so here, kind of very lame or simple example is that those two processes are executing two independent bootstrap replicate searches. Right. So now, talking about phylogenetics, here are some memory challenges. So if you think about supermatrix approaches, where we just concatenate the genes of the species we study, it's maybe not the only way to do it, but the memory footprints for those data sets are becoming huge. So here's like a little history of how large they've become. So in 2011, Ziying Yang had a data set that required 190 gigabyte of memory to be able to compute the likelihood on this data set. Then in 2014, we already required 1 terabyte to analyze of main memory to analyze 140 insect transcriptomes. Then in 2017, we estimated that we would require 7 to 8 terabyte for analyzing 1,600 insect transcriptomes. And then finally in 2019, this is an analysis we just ran a couple of months ago, we required 9 terabyte of main memory of RAM for analyzing 350 bird genomes and 500,000 core hours, so 500,000 processor hours, for just computing a single maximum likelihood tree. So this is kind of totally getting out of control, like the memory footprints and time requirements for those very large scale phylogenomic analysis. So what are the solutions here? There are a couple of algorithmic means and advanced data structures that we can use to reduce the memory footprints and also accelerate the calculations. We can also, we have to use supercomputers, so that's kind of the brute force approach, just use large enough systems such that you can conduct or carry out such runs, or simply you just don't infer trees on such supermatrices, right? So you can use gene tree, species tree reconciliation methods, or maybe with the argument that you have such a huge amount of data and you should have such a clear signal, you can use discrete methods like k-mirrors and apply them on whole genome alignments instead of using likelihood. So here's like just an example paper of how this could be done. So you try to use maybe simpler methods because you have so much data. You would want to use simpler methods to analyze the data. And so one thing we're going to do is that we're actually going to derive a formula for calculating the memory required to compute the likelihood on an alignment of a given size of n taxa and m sites. So we'll do that later on. Okay, so here's part number 2, just like a quick review of maximum likelihood calculations. Okay, so let's recap likelihood calculations. Just to provide you an overview of how that works, so we're given our multiple sequence alignment with a length of m. Then we're given our substitution model, so which is commonly denoted as the Q matrix, that gives us the transition probabilities or transition rates for time dt. And then for computing the transition probabilities on real times t, we need to exponentiate this rate matrix, so it's it's a matrix exponential e to the power of q times t. The other thing that we need are the prior probabilities or empirical base frequencies, so those can either be derived or either given by the model, right? So Jukes Cantor just assumes that all are 0.25, or you can use empirical base frequencies essentially by counting the frequency of occurrence of A, C, G, and T in the alignment, or you can do a maximum likelihood estimate of those frequencies, treating them as free parameters. Then we're given our phylogenetic tree with the sequences located at the tips and branch lengths assigned to all branches of the tree. Then, as I said before, as we've seen before, we place a virtual root onto that phylogenetic tree to define a traversal order, and then using the Felsenstein pruning algorithm actually start filling up those conditional likelihood vectors that have the same length as the alignment, and per alignment column we store the probability of observing an A, C, G, or T conditional on the respective subtree that those conditional likelihood vectors actually summarize. Right, so this is our main problem, right? So filling those vectors is both floating point intensive and memory intensive. So the space, the memory space we need for storing those conditional likelihood vectors dominates the memory requirements of maximum likelihood programs. A nice thing here, a nice observation here, like a good thing about the model, is that we assume that our sites evolve independently, and this actually means as a consequence that we can compute the per site log likelihoods in parallel, right? So in an ideal world, if I have an alignment with 1,000 sites, I could use 1,000 processors to calculate the likelihood on such an alignment and a given tree. But of course there would be a huge synchronization overhead. But in theory, this is what I could do. Right, and then as I said, we do a post-order traversal. As I've shown you previously, we do a post-order traversal of the tree, starting at the virtual root. And here, once we are at the tips, we initialize the tip vectors like this, right? Like an A is just a conditional likelihood vector of a 1.0000. G has a 1.0 at the third position, etc. So the way the conditional likelihood vectors at the tips look like, this is kind of very simple, always has this form here. Then we continue our traversal, and every time we visit an inner node for the last time, we can actually compute its conditional likelihood vector. And so this is what this calculation looks like. So if we just consider that we want to compute a conditional likelihood vector here at an inner node that is connected to two child vectors via branch bi and bj, whose values have already been computed, what we need is a transition probability matrix given the respective branch lengths bi and bj, and then at position k of our alignment, we this is not, should this be position k? No, at position c of our alignment, sorry, we fill in this, we start computing the conditional probability of A, and so this is, well, A could